the last class, towards the end, we were discussing about the impedance matching. Before that, we discussed about Smith chart. What is Smith chart we discussed. Then how to obtain or how to represent an impedance on the Smith chart or a admittance on the Smith chart, that we discussed. Then once we represent an impedance or an admittance, then how to find out the Vhwr, the reflection coefficient, the point from the load where the voltage will be maximum on the line, the distance from the load where the voltage will be minimum from the line. All those things we discussed, how to find out those things, that we discussed about using Smith chart. So we have a general understanding of the Smith chart and its simple uses of Smith chart that we saw first. Then we came to the impedance matching. What is impedance matching? That is what we discussed. Why impedance matching is important, that we discussed. Then we saw there can be three situations. One situation is a real impedance is to be matched to a real impedance. Then we saw that a real impedance is to be matched to a transmission line. Then we saw that two infinitely long transmission lines of different characteristics impedance have to be matched. These are the three situations that we saw. We started with the first one, in which we tried to match the real impedance to a real impedance, and for that we saw that this quarter wave transformation is the simplest technique. It's a very simple technique. Using quarter wave transformation, we can match one impedance to other impedance when both are resistive or both are real. So two real impedances can be matched using quarter wave transformation. That we saw. Now, today we will extend that knowledge what we discussed in the last class. We will see that or we will investigate, is it possible to match a complex load, which means the impedance is complex. So impedance is not purely real. Impedance is not purely resistive. Impedance has a resistive part as well as impedance has a reactive part. So if we have such a load impedance which has a resistive part as well as a reactive part, can we match that load impedance to a real impedance or to a purely resistive part? For example, suppose we have a transmission line of characteristics impedance Z0, and the transmission line of characteristics impedance Z0 is terminated on a load impedance ZL, which is equal to R plus JX. Now R plus JX is different from Z0, and we are required to match R plus JX to Z0. Is it possible? We know that if R plus Jx, when we consider if X is equal to 0, then we can use a quarter wave transformation. So we will use a quarter wave transformer, which is a transmission line section of length lambda by 4 or quarter wave length transmission line section with characteristics impedance Z0X is equal to root over of R into Z0. That we know. But now we have R plus Jx instead of R, we have R plus Jx. then we cannot have a characteristic impedance Z0x which is equal to root over of Z0 into R plus Jx. So R Z0 into R plus Jx whole root over. That will be difficult to find out that root over is difficult. It will be a complex number. Then we will have a characteristic impedance which is complex. That again is difficult. Usually the characteristic impedance of a transmission line will be taken to be real. The imaginary part will be always neglected. It will be negligibly small. So that part will not be there. So in that case, in such a situation, can we design some method by which we can match R plus Jx to Z0? We know we can match R to Z0. So if we can transform R plus Jx to R, somehow we can transform R plus Jx to R, then we can use, then we can match R to Z0. That is possible. That we know that we can use quadratic transformation to transform R to Z0. That we can do. Now the question is, can we transform R plus Jx to R? So to do that, we require the help of a Smith chart. We can do this. Once we use a Smith chart, you will know how to do that. And as we discussed, when we are using Smith chart, we are always dealing with normalized impedances. So let us first normalize the impedance R plus Jx, which is ZL. Let us first normalize the ZL with respect to some arbitrary impedance Z01. So small ZL is equal to R plus Jx or capital ZL divided by Z01. Let us write that as small r plus J small x. So small ZL is equal to small r plus J small x. So that is the first thing that we will do using when we are going to use a Smith chart. So what we will do after that, once we have normalized that, we will locate this point R plus Jx point. We will locate on this Smith chart. Okay, and now, so take a Smith chart. On this Smith chart, locate the point P on this Smith chart so that P represents the point ZL is equal to R plus Jx. How can we locate P? First, we will identify the constant resistance circle which corresponds to small r. So first identify that circle. Then we will identify the constant reactance R. Since here it is plus Jx, so it will be in the upper part. There are two parts, upper part and lower part. It will be in the upper half. In the upper half, we locate where is the Jx, x part. What is x? So find out that x, then follow the arc corresponding to the x, and find out the point P where this arc meets the constant resistance circle. So that is the point. That is how we locate the point P. Once we have located the point P, then we will draw the Vhwr circle. So how do you draw the Vhwr circle? Take the center of the Smith chart, which is how to identify the center of the Smith chart, and look at the constant resistance line, which is the horizontal line. On the horizontal line, below the horizontal line, there are numbers. Look at those numbers. Locate the number which is equal to 1. Locate the number 1. That is the center of the Smith chart. So on the horizontal line, locate the point which corresponds to the value 1. Take that as the center. From that point, take a radius up to the point P. That is the radius of the VSWR circle, then draw the VSWR circle, which will pass through point P with center at 1. Once we draw the VSWR circle, we know that on a transmission line, VSWR is fixed. Every point on the transmission line will give us the same VSWR because it is Vmax by Vmin. So it will Vmax by Vmin. So we will always get same VSWR. Therefore, we draw a constant VSWR circle. Any point on the transmission line is going to give us constant VSWR and constant amplitude of the reflection coefficient. Any point on the transmission line is going to give us. Now, if from point P we move along the constant VSWR circle, so then we can reach 2 points, 2 important points. One point is the first point. So now point P is representing the load, and if we move in the clockwise direction, we will move towards the generator or towards the source. So from point P, move in the clockwise direction till we reach the horizontal line. Till we reach the horizontal line. Okay. So we will do that later. I will tell you what to do that. Now, before moving that in that direction, what we can do is we can join the center of the Smith chart to the point P and extend it. So from the center, join point P, then extend a line, and that cuts the Smith chart at the outer perimeter. So it goes out. So it goes to the rim of the Smith chart. It goes out of the Smith chart and extend this line. Then what we will do is move from point P to the point Q. Q is the point on the horizontal line where the constant VSWR circle meets the horizontal line. So locate the point Q where the constant VSWR circle meets the horizontal line. Now at point Q, as you can see, on the horizontal line, the impedance is purely resistive. Therefore, at point Q, the impedance is purely resistive. Impedance will no longer be complex, it will be purely real. So from point P, move to Q. Now, how to find out how much distance we have moved? That is why we have extended from center through point P a line to the outer rim. Now you can see that there is an arc outside the Smith chart. You can see there is an arc with 2 arrows on both the ends, which is connecting this arc is from point P, the line which is passing through point P, to the line to the horizontal line. Between them there is an arc. So at the two ends of the arc, at one end, that is the point Q end, at that end the wavelength is 0.25 lambda, because it starts from 0, goes to 0.25, then comes back to 0.5, which is reset to 0. So starts from 0, goes to 0.25 after 180 degree, then after 360 degree it is 0.5 lambda, that is reset to 0. So from P to Q, we will find out what is P to Q. So from 0 go up to P, read the value. What is the value for P on the outer ring? Read the value for P. Wavelength, it will be in wavelength. For P, read the value where this line coming which is passing through P meets the outer ring, and the outer ring read the value. That will give the wavelength of P. For P, you will get a wavelength. Then from P, move to Q. Q will be 0.25. Therefore, total length from P to Q, wavelength in terms of wavelength, total wavelength or total length from P to Q will be 0.25 lambda minus whatever lambda is for P. So that difference will give us the length of a transmission line section, so which will transfer the impedance to a pure resistance. So you have R plus Jx representing Q, P. You want to come to Q. So for that, we have to use a section of transmission line. The length of the section of transmission line is the length in terms of wavelength. If you move from P to Q, so use that. Use the transmission line of that section. So find the distance L in wavelength from P to Q by taking the difference from the outer circle moving towards the generator along the rim of the swing jack. So once you have done that, then we will find out what is the real value of the impedance at the end of this transmission line section N. So that real value will be equal to this Z01, which is the characteristic impedance of the line section, into R. R is the resistance value at Q. So resistance value, whatever is the resistance value on the horizontal line, so read that resistance value at Q, then multiply that with Z01, that gives us Z1, which is the real value, real Z1. So once you find out real Z1, then we can use a quadratic transformer to match that real Z1 to Z0, which means we will have a quadratic transformer of characteristics impedance Z0x, which is equal to square root of Z0 into Z1. So P can be matched, a complex impedance can be matched to a real impedance by using two sections. One is a transmission line of appropriate length, which is converting the complex impedance to a real impedance. Then we have a transmission line of quarter wave length, which is making a quadratic transformation. This is one method. Then let us look at another method. Same method, let us look at another way of solving this. So, alternatively, from P, instead of moving up to Q, continue moving along the Vhwr circle till you reach the point S. Look at this. Look at the figure. So from P we have moved to Q earlier. Now in the alternative solution, move to the point up to the point S. So what will be that distance? If you move from P to S, then at S again the resistance is purely, the impedance is purely resistive. The impedance is purely resistive at 2 points. One point is Q, other point is S. So for Q we have found the solution. Now you move up to S. So then what we will do, how to find out the length of the transmission line section, which is from P to S. When you move from P to S, what will the equivalent section length, length of the transmission line section? So that length will be, again you can see the outer arc. In the outermost circle there is an arc which is from P to S. How to find it out? So you have found out P to Q, take that P to Q value, then add to that 0.25 lambda. P to Q length we have found out, so that plus 0.25 lambda, because you have from Q to S we are moving a distance of 0.25 lambda t, actually 180 degree. Since we are moving from Q to S, we are moving an angle of 180 degree, which is equivalent to 0.25 lambda. So add 0.25 lambda to the previous one. So that will give us this. So once you find out that, then find out what is Z1. Z1 will be equal to Z01 divided by R at S. Remember, this is important. Z1 is equal to Z01 divided by R at S. Why? In the previous case, it was Z1 is equal to Z01 into R at S. If you go to the minimum point, then it is Z01 divided by R at S. So this is the difference. Otherwise, everything is same. So with this, we came to conclusion, or we came to end of matching different types of impedances, pure resistance with pure resistance, and impedance with resistance. Both these we have come to, we have discussed. So after this, let us take a break here for 5 minutes. Then we will come back and discuss important things. I will now advise you that if you have your Smith charts ready with you, come with Smith charts. Keep Smith chart ready with you. Keep your compass box ready. We will do some hands-on now. What we will do is now we will do matching circuits using lump derivatives. So we will discuss about matching circuits using lump derivatives.